You think you understand fire. That's your first mistake. And I want you to sit with that for a second before I say another word. You've been lighting stoves and starting campfires your whole life. And somewhere along the way, you decided you understood the basic principle. Something burns, heat comes out. End of story. And I get it. That explanation works fine when you're trying to cook a steak. But the moment you try to use that same mental framework to understand what happens inside a nuclear reactor, or inside the core of a hydrogen bomb, or inside the sun, that framework doesn't just bend, it shatters. And what's left after it shatters is something so much stranger and so much more beautiful than fire that I genuinely do not understand why we don't teach it to every human being on Earth before we let them graduate high. School. So let's start over. Let's start from absolute zero, not temperature, but assumption. Pretend you know nothing. Pretend we're in a room with no history, no received wisdom, no half-remembered high school chemistry, because here's what I've learned after 50 years of doing this. The people who understand atomic energy the least are usually the ones who think they already understand it. They've got a picture in their head, atom splitting, big explosion, mushroom cloud, and that picture is not wrong exactly, but it's so incomplete that it might as well be wrong. I'd rather have a student who knows nothing than a student who knows the wrong thing confidently. At least the empty cup can be filled. So here is the question I want you to hold in your mind for the next hour. Not, what is atomic energy? That's a textbook question. Here is the real question. Why does matter contain energy at all? Why should a piece of uranium sitting on a table, doing nothing, just sitting there, contain enough energy to level a city? Where is that energy hiding? What is it doing in there? And why does releasing it require something as violent and specific as splitting an atom rather than, say, just warming the uranium up a little? These are not rhetorical questions. These are the questions that kept the greatest physicists in history up at night, and getting to the answer requires us to rebuild our picture of matter from the ground up. So that's what we're going to do. Let me start with something that sounds simple and isn't. Everything you see, this stage, those seats, your own hands, is made of atoms. You've heard this. You think you know this, but do you really feel it? An atom is almost entirely empty space. The nucleus, the dense, heavy core, where almost all the mass lives, is so small relative to the whole atom that if you blew the atom up to the size of a football stadium, the nucleus would be the size of a marble sitting on the 50-yard line. Everything else is empty. The electrons orbiting out at the edge of that stadium are so light they barely register as mass at all. So when you look at this podium and you think you're seeing solid wood, what you're actually seeing is an almost completely empty collection of tiny marbles surrounded by vast howling nothing, held in formation by electrical forces you cannot see. The solidity is an illusion constructed by those electrical forces. The wood does not want you to put your hand through it, and so you can't. But the emptiness is real. Now, inside that marble, inside that nucleus, is where things get interesting. The nucleus is made of protons and neutrons packed together extraordinarily tightly. Protons carry positive electric charge. And here is where your common sense should already be screaming at you. Positively charged particles repel each other. That's basic electromagnetism, something we've known since Coulomb in the 18th century. Like charges push each other away. So why doesn't the nucleus just explode? Why doesn't every atom in the universe fly apart instantly? If I put 100 positively charged protons in a box this small, the electromagnetic repulsion between them should be catastrophically violent. They should scatter in every direction. And the answer is that there is a force in nature that you were probably not taught to take seriously in school, and it is the most powerful force in the known universe. We call it the strong nuclear force. And it is, in the most literal physical sense, what holds the world together. The strong force acts between protons and neutrons at extraordinarily short ranges. We're talking distances of about a femtometer, which is 10 to the minus 15 meters, a distance so small that calling it small is a grotesque understatement. And at those ranges, it is roughly 100 times stronger than electromagnetic repulsion. So the protons are screaming at each other electromagnetically, trying to fly apart, and the strong force is grabbing them and saying, no, not today. You're staying together. Now, here is where it gets strange. And I mean that literally not as a rhetorical device, not as a way of making the material feel exciting. It genuinely gets strange here. And if you are not feeling a little disoriented right now, you haven't been paying close enough attention. The strong force holds the nucleus together, but holding things together costs something. Or rather, and this is the key insight, holding things together saves something. When protons and neutrons bind together into a nucleus, the resulting nucleus is slightly less massive than the sum of its individual parts. This is not a rounding error. This is not a measurement artifact. The bound nucleus genuinely, physically weighs less than the separated nucleons did individually. Mass disappears. And Einstein told us in 1905, in a 3-page paper that might be the most consequential 3 pages ever written in the history of science, that mass and energy are the same thing, related by the speed of light squared, E equals mc squared. That missing mass didn't vanish. It was converted into the energy that holds the nucleus together. It became binding energy. It became the glue. Let me give you a thought experiment to make this concrete, because I think the abstraction obscures how genuinely astonishing this is. Imagine you have a proton and a neutron floating freely in space, not yet joined. You measure their total mass very carefully. Now you let them come together and form a deuteron, the nucleus of deuterium, heavy hydrogen, and you measure the mass again. The deuteron is lighter by a tiny but completely real and measurable amount. That missing mass is the binding energy, and it was radiated away as a gamma ray photon when the nucleus formed. The universe paid you back in light for the act of assembly. And if you want to break the deuteron back apart, if you want to separate the proton and neutron again, you have to put that energy back in. You have to pay the universe back for what it gave you. That's what binding energy means. It is the energy cost of togetherness. Now, different nuclei have different amounts of binding energy per nucleon, per proton or neutron, and this is where the engineering of atomic energy lives. There is a curve, physicists call it the binding energy curve, and it is one of the most important graphs in all of science. On one end, you have light nuclei, hydrogen, helium, lithium. On the other end, you have heavy nuclei, uranium, plutonium, thorium. And in the middle, around iron and nickel, you have the nuclei with the highest binding energy per nucleon, the most tightly, efficiently bound nuclei in nature. Iron is, in a very specific sense, the most stable thing in the universe. It is the bottom of the nuclear energy valley. Here is what that curve means for energy. If you take a heavy nucleus, say uranium, 235, and you split it into 2 medium-sized pieces, both of those pieces sit higher on the binding energy curve than iron, but lower than uranium. They are more tightly bound per nucleon than uranium was, which means the products are lighter than the original nucleus, which means mass has been converted to energy. That's fission. That's the atomic bomb. That's every nuclear reactor that has ever run. The energy comes from the fact that the pieces are more tightly bound than the whole, and the binding energy that gets released, the difference in mass, multiplied by the speed of light squared, comes out as kinetic energy of the fragments and as radiation. It is not chemical energy. It is not rearranging electrons. It is rearranging the nucleus itself and releasing the energy that the strong force was holding in store. But now look at the other end of the curve. If you take 2 very light nuclei, 2 isotopes of hydrogen, say deuterium and tritium, and you fuse them together into helium, the helium nucleus is more tightly bound per nucleon than the hydrogen nuclei were. Again, the product is lighter than the parts. Again, mass becomes energy. That's fusion. That's the hydrogen bomb. That's the sun. The sun is not burning in any chemical sense. There is no combustion happening in the core of the sun. The sun is fusing hydrogen into helium, and the mass difference is being radiated outward as sunlight, and has been for 4.5 billion years. Every photon of light that has ever warmed your face is the product of nuclear fusion. Every time you've stepped outside on a sunny day, you've been standing in the exhaust of atomic energy. You just didn't know what you were standing in. Now, I want to stop here and tell you something about my own history with this problem because I think it matters. When I was a young physicist, still a graduate student, I had a conversation with one of my professors. I won't embarrass him by naming him. He's still alive, about the binding energy curve. And he explained it to me the way it was usually explained then, which was essentially the mass defect is a consequence of special relativity, E equals mc squared, end of discussion. And I accepted that. I wrote it down, I passed my qualifying exam, I moved on. And it nagged at me. For years it nagged at me. Because E equals mc squared tells you that mass and energy are equivalent. It gives you the exchange rate, but it doesn't tell you where the energy is coming from. It's like knowing the conversion rate between dollars and euros without knowing why your wallet is lighter after you bought something. The accounting works, but the physics felt incomplete to me. What I eventually came to understand, and this took years and several wrong turns, and a conversation with Murray Gell-Mann that I'll never forget, is that the binding energy is not just a consequence of special relativity in some abstract sense. It's a consequence of the quantum mechanical structure of the strong force. The quarks inside the protons and neutrons are themselves held together by gluons. The carriers of the strong force and the energy of that gluon field is enormous and complicated and contributes to the mass of the proton in ways that are still being computed on supercomputers today. The proton's mass does not come primarily from the mass of its constituent quarks. Most of it comes from the energy of the gluon field binding those quarks together, which means most of the mass of everything you have ever touched comes from energy, not from stuff, from the energy of confinement, from the energy of a force holding things together. That realization that mass is mostly a manifestation of energy rather than the other way around changed how I think about everything. And I tell you this not to brag about an insight, but because I spent years not understanding it clearly, and I want you to know that the confusion you might be feeling right now is not stupidity. It is appropriate. This stuff is hard. Anyone who tells you it is easy is not doing you a kindness. They are robbing you of the genuine experience of understanding something real. Let me talk about fission more carefully, because this is where the history becomes dramatic in ways that the textbooks don't fully convey. By the 1930s, physicists knew the nucleus existed. Rutherford had established that in 1911 with his famous gold foil experiment. He shot alpha particles at gold foil and found that some of them bounced back, which could only happen if the positive charge in an atom was concentrated in a tiny, dense core rather than spread throughout the atom like a pudding, as the previous model had assumed. That discovery, incidentally, is one of my favorite moments in all of science, because Rutherford himself described finding the bouncing back alpha particles as if you'd fired artillery shells at tissue paper and had them come back and hit you. The surprise was that total. The implications were that enormous. Then in 1932, James Chadwick discovered the neutron, the electrically neutral particle in the nucleus. And suddenly, physicists had a tool. You see, if you want to probe a nucleus, if you want to poke it and see what happens, charged particles are difficult to work with because they get repelled by the positive charge of the nucleus before they can get close. But a neutron has no charge. A neutron can walk right up to a nucleus and knock on the door without getting pushed away. And when Enrico Fermi in Rome in 1934 started systematically firing neutrons at every element he could get his hands on, he began to see unexpected transmutations. Elements were changing into other elements. He didn't know at the time what was happening. He thought he might be creating elements heavier than uranium, transuranic elements, and he won the Nobel Prize partly on that basis. He was wrong. Or rather, he was right that something interesting was happening, but he had misidentified what it was. What was actually happening, what Lise Meitner and Otto Hahn and Fritz Strassmann figured out in 1938, in a set of experiments that constitute one of the most consequential Christmas breaks in the history of science, was that uranium-235, when struck by a slow neutron, was splitting, not transmuting into something heavier, splitting, breaking into pieces, barium and krypton, two medium-sized nuclei from one large one, with a release of energy that was, by chemical standards, obscene. Meitner did the calculation walking through the snow in Sweden. She had fled Nazi Germany by this point. Let's be clear about the historical context here. And she figured out that the energy released per fission event was about 200 million electron volts. A typical chemical reaction releases a few electron volts. She was looking at something 100 million times more energetic, gram for gram, than anything chemistry could produce. And here is where it gets strange again. Here is where the thing goes from being a laboratory curiosity to being the defining fact of the 20th century. When uranium fissions, it doesn't just release energy, it releases neutrons, 2 or 3 of them on average. And those neutrons can go on to strike other uranium nuclei, causing them to fission, releasing more neutrons, which strike more nuclei. And if you have enough uranium in a small enough space, you get a chain reaction. Each fission event triggers more fission events, and the reaction multiplies exponentially. In a nuclear reactor, you control that chain reaction, you keep it right at the edge of criticality, where each neutron causes exactly 1 more fission on average, and you extract the heat to boil water and drive turbines. In a bomb, you let it go supercritical. You let the chain reaction multiply without constraint for the millionths of a second it takes for the energy release to become incomprehensible. That's all the difference there is between a power plant and a weapon. It is a difference of engineering and control, not a difference of physics. Fermi built the first nuclear reactor under the stands of a squash court at the University of Chicago in December of 1942. He called it Chicago Pile 1, which is possibly the most understated name ever given to a world historical artifact. It was a pile of graphite blocks and uranium with cadmium control rods that absorbed neutrons and could be pulled out to let the reaction proceed. And when the rods came out far enough, the Geiger counter started clicking faster and faster, and Fermi looked at the numbers and said, and I am paraphrasing here, but barely, the reactor is self-sustaining. Someone opened a bottle of Chianti. That was the celebration. A bottle of Chianti passed around in paper cups on the day that humanity first controlled the energy of the atomic nucleus. I find that detail simultaneously charming and terrifying, which I think is the appropriate response. Now, I want to address something that I know is sitting in the back of your mind, because it sits in the back of everyone's mind when we talk about nuclear energy. The bomb, Hiroshima, Chernobyl, 3 Mile Island, Fukushima. I know those words are in the room right now, and I'm not going to pretend they aren't. Because part of understanding atomic energy, really understanding it, not just the physics, but the full human reality of it, is understanding why it inspires such fear and whether that fear is calibrated correctly. Here is what I believe. And I want to be clear that this is not just scientific opinion, but a conclusion I've reached after decades of thinking carefully about it. Our fear of nuclear energy is real and historically understandable, but it is not always well calibrated to the actual evidence. Let me be precise. Nuclear weapons are genuinely, specifically, existentially terrifying, and the fear of them is entirely rational. 2 cities were destroyed in the space of 3 days in 1945. We built enough warheads during the Cold War to kill every human being on Earth several times over. That fear is earned. I will not minimize it. But civilian nuclear power is a different question. Every energy source kills people. Coal kills people through air pollution at a rate that is staggering, and largely invisible estimates run into the millions per year globally when you include the full chain from mining to combustion to particulate inhalation. Natural gas pipelines explode. Hydroelectric dams collapse. Wind turbines kill installation workers. The question is never whether a technology has zero risk, because no technology has zero risk. The question is comparative. And when you do the comparison, honestly, deaths per terawatt hour of energy produced, including accidents, including radiation exposure, Including everything, nuclear power is one of the safest energy sources ever deployed by human civilization. Chernobyl was a real disaster. Fukushima was a real crisis. The total death toll from civilian nuclear power globally across decades is measured in the thousands. Coal kills that many people every few days. I'm not saying this to minimize the real suffering caused by nuclear accidents. I'm saying this because the truth matters. And the truth is that our collective intuition about comparative risk is badly distorted by the way we process information about catastrophic versus diffuse harm. This is actually something I find genuinely and productively unsettling, not the nuclear risk itself, but the epistemological problem it represents. We are not very good at comparing risks across different domains of experience. We are terrified of rare dramatic events and blind to common, slow-moving ones. A nuclear accident appears on the front page for weeks. Coal pollution killing people quietly every day appears on no front page at all. I don't know how to fix that about human cognition, and I'm not sure it can be fixed completely. But I think part of what science education should be doing, part of what any education should be doing, is equipping people to notice the gap between their intuitive risk assessments and the actual numbers. Because policy decisions made on the basis of miscalibrated fear are genuinely dangerous, and the history of energy policy is full of them. Let me come back to the physics for a moment, because I want to make sure we've covered fusion, and I want to make sure we've covered it honestly, because fusion is currently one of the most exciting and most overhyped topics in all of applied physics, and those two things can coexist. Here is the basic physics of fusion, stated as cleanly as I can state it. The light nuclei hydrogen isotopes primarily have low binding energy per nucleon. If you can force them together close enough for the strong force to grab them, they will fuse into helium, and the helium nucleus is more tightly bound, and the mass difference comes out as energy. The energy yield per unit mass is even greater for fusion than for fission. A gram of deuterium-tritium fuel contains more energy than a gram of uranium-235, and the fuel is extraordinarily abundant. Deuterium is found in ordinary seawater. You can extract it from the ocean essentially without limit on any human timescale. Tritium is rarer, but it can be bred from lithium, which is also widely available. And unlike fission, fusion produces no long-lived radioactive waste. The main product is helium, which is inert. The reactors themselves become mildly radioactive over time from neutron bombardment, but the waste problem is orders of magnitude more manageable than with fission. So why don't we have fusion power? The answer is that forcing nuclei together is extraordinarily hard. Those nuclei are positively charged, and they repel each other electrostatically, the Coulomb barrier, and to get them close enough for the strong force to act, you have to give them enough kinetic energy to overcome that barrier, which means you need to heat the fuel to temperatures of around 100 million degrees Celsius. The sun does this through gravity. Its core is under such immense gravitational pressure that the temperature and density are sufficient to maintain fusion continuously. We cannot replicate that gravitational pressure on Earth. We have to substitute something else for it, and the two main candidates are magnetic confinement using powerful magnetic fields to contain a hot plasma in a donut-shaped vessel, and inertial confinement, where you compress a small pellet of fuel so rapidly with lasers that it fuses before it has time to fly apart. The problem that has haunted fusion research for 70 years is elegantly summarized in a joke that has been circulating among plasma physicists since approximately 1960. Fusion power is 30 years away and always will be. It is a cruel joke, and like all the best cruel jokes, it contains a genuine insight. Magnetic confinement in particular has been plagued by instabilities. The hot plasma finds ways to wriggle out of the magnetic bottle faster than the theory predicts it should, and the engineering of a system that confines plasma reliably at sufficient density and temperature for long enough to produce more energy than it consumes has proven extraordinarily challenging. Now, here is where it gets strange, for the third time, because something has genuinely changed in the last decade. And I want to be careful here to distinguish real progress from hype, because the history of fusion is littered with announcements that did not pan out. But the combination of high temperature superconducting magnets, which allow you to build much stronger and more compact magnetic confinement devices than was previously practical, and a genuine influx of private capital and engineering talent, has pushed the timeline estimates among serious physicists, not press release physicists, serious ones, into a range that feels qualitatively different from the previous 70 years of almost there. I am cautiously optimistic, and I want to emphasize the word cautiously, because optimism in fusion research has a long and painful history of being premature. But let me tell you what success would mean, because I don't think it has been stated clearly enough in public discourse. If we achieve commercial fusion power, power that is cheaper than fossil fuels generated from seawater, producing no carbon dioxide and no long-lived radioactive waste. The implications are not just significant, they are civilizational. Energy scarcity is the root constraint on almost every large-scale problem humanity faces. Freshwater scarcity can be solved by desalination, which is an energy problem. Food production at scale is an energy problem. Industrial manufacturing is an energy problem. Poverty, in many of its material dimensions, is an energy problem. A world with effectively unlimited clean energy is a world that looks fundamentally different from the one we currently inhabit. I am not saying this to make fusion sound magical. It will not solve political problems. It will not resolve conflicts over power and resources. It will not make human beings suddenly wise. But it would remove a constraint that has shaped the trajectory of human civilization since before we were fully human, and what comes after the removal of that constraint is genuinely unimaginable, and I mean that in the literal sense. Let me now take a step back and connect what we've been talking about to something even larger, because this is the thing about physics that I find most humbling and most exciting. Every time you pull on one thread, you find that it is connected to everything else. The binding energy of nuclei is real. We've established that. Mass becomes energy, energy becomes mass. The strong force is the most powerful thing in nature at short range. But underneath all of that, underneath even the quarks and gluons and the quantum field theory that describes the strong force, there is a question that is not yet answered. It is the question of why there is any matter in the universe at all. In the first moments after the Big Bang, matter and antimatter should have been produced in exactly equal quantities. When matter meets antimatter, both are annihilated. If the symmetry had been perfect, the universe would contain nothing but photons light with nothing to illuminate. The fact that you are sitting here, made of matter, is evidence that the symmetry was broken. Somehow, in the earliest moments of the universe, for reasons we do not fully understand, matter won by the smallest of margins. Roughly one extra particle of matter for every billion matter-antimatter pairs that annihilated. Everything you see, every galaxy, every star, every atom in your body is the residue of that tiny asymmetry, and we do not know why it happened. The physics of atomic energy, the strong force, the binding of nuclei, this is well understood, tested, verified, applied. We have been splitting atoms for 80 years. We know how to do it. But the question of why there is matter for the atoms to be made of that question leads straight to the frontier of physics, to experiments at CERN and beyond, to theoretical frameworks that are not yet confirmed, to a gap in our understanding that is not a minor technical detail, but a fundamental mystery about the structure of reality. I've spent my career at the boundary between what we know and what we don't. That boundary moves. When I started in physics, the standard model of particle physics did not yet exist in its current form. The quark model was still controversial. The gluon had not yet been experimentally confirmed. The idea that the proton had internal structure was, within living memory, a radical claim. Now these things are textbook material taught to undergraduates, no longer surprising. The boundary has moved. And what is at the boundary now? The nature of dark matter, the matter-antimatter asymmetry, the question of whether there are more forces and more particles beyond what the Standard Model describes, these things will also eventually become textbook material. The boundary will move again. It always does. But here's what I want to leave you with, and I want to say it carefully because I think it is often said carelessly. The fact that the boundary moves, the fact that we have learned so much, that we have gone from not knowing atoms existed to splitting them in the space of a century, this does not mean that everything is figured out, or that the process of figuring things out is winding down, or that what remains is merely tidying up. The questions at the frontier today are not smaller or less fundamental than the questions that were at the frontier 100 years ago. In some ways, they are more fundamental, and the process by which we answer them, the building of better instruments, the construction of more precise theories, the willingness to be wrong and to start over this process is not finished. It is very much alive. Here is the thing about atomic energy that I think does not get said enough in public discussions about it. It is a demonstration of the power of understanding. Not just applied understanding, not just the engineering, but the pure theoretical understanding that came first and made the engineering possible. Einstein did not derive E equals mc squared because he was trying to build a bomb. He derived it because he was trying to understand the relationship between space and time. Rutherford did not perform the gold foil. He was trying to understand the structure of matter. Meitner did not figure out fission while trying to design an energy source. She was following the data wherever it led, with rigor and without agenda. And then, because the understanding was real, because the equations actually described something true about the universe, the engineering became possible. The reactor became possible. The applications for good and for terrible ill became possible. This is the pattern. This is always the pattern. Pure curiosity, followed by rigorous understanding, followed by the world-changing applications that the people doing the pure research could not have predicted and often did not seek. This should make you think very carefully about arguments that science funding should be directed only toward immediately practical goals. When you tell a physicist, don't bother figuring out the structure of the atom unless you can tell me what it's useful for, you are revealing a profound misunderstanding of how the most powerful knowledge in human history has actually been generated. The answers to what is this thing made of and why does the universe work this way are the most practically consequential questions in science. They just don't look that way until after the fact. I have spent a lifetime doing this work, and I will tell you what I believe. I believe that understanding the physical world, really understanding it, not the cartoon version, not the metaphor, but the actual mathematics and the actual experiments and the actual verified truth, is one of the highest activities a human being can engage in. Not because it makes us powerful, though it does, not because it makes us comfortable, though sometimes it does that too, but because it is true, because the universe actually works this way, because the same equations that describe the binding energy of a uranium nucleus also describe the light from a star a billion light years away. Because we live in a cosmos with laws, and those laws are knowable, and we have found them, and we keep finding more of them, and that fact is extraordinary. The uranium in a nuclear reactor is doing nothing mysterious. It is doing what physics says it must do, releasing the binding energy stored in the strong force when its nucleus is cleaved apart by a neutron. The sun is doing nothing supernatural. It is doing what physics says it must, fusing hydrogen into helium under gravitational pressure, converting mass to energy at a rate that has been sustaining life on this planet for billions of years. The equations are real. The numbers check out. The predictions match the measurements to extraordinary precision. And yet, sit with this for a moment. We do not fully understand where the matter those nuclei are made of came from. We do not know why the symmetry between matter and antimatter broke the way it did. We do not know, in the deepest sense, why there is something rather than nothing, why the laws of physics take the form they take rather than some other form or no form at all. The architecture of atomic energy is well mapped. The foundations on which that architecture rests are not. So here is what I want to leave in your chest. Not a conclusion, not a comfort, a question. Every atom in your body was forged inside a star, not our star, but ancient stars that died before our solar system existed, that fused hydrogen into heavier elements over billions of years, and then scattered those elements across the galaxy in supernova explosions. You are the product of stellar nucleosynthesis. Your iron, your calcium, your carbon, all of it was made by the same process I've been describing tonight. Fusion in stellar cores, and then scattered by stellar death, and then assembled by gravity and chemistry into you. You are, in the most literal physical sense, made of exploded stars, and yet you do not know why you are here instead of nothing. You do not know why the universe that produced you by this extraordinary sequence of physical processes governed by these beautiful and precise laws chose to produce anything at all. That question is not answered. It may not be answerable. And I find that not comforting but clarifying. It means we are not done. It means the work continues. It means the argument is still open. And anyone who tells you it is closed is either fooling themselves or trying to fool you. Go home and think about that. I'll be thinking about it too.